All right, section 14.1, we talked about measurement. Do you remember specifically what kind of measurement we were using in 14.1? Length, linear, right. We were measuring the length of things. It's called linear measurement. So what we're going to be doing today is a different kind of measurement. It's going to be area measurement. And specifically, we're going to look at the area of polygons and circles. So area is defined as the number of non-overlapping squares of a particular size that cover a region. Area is always measured using square units. So if we're looking at this particular square that's on the screen, and this is 1 unit here, whatever that unit measurement is, and this is 1 unit here, then we would say that the area of the shape inside would be 1 unit squared. And we actually read that as 1 square unit. So it looks like we're writing down units squared every time. So feet squared, meters squared, whatever it is squared. And we read the word squared before we read the linear unit that we would have been using before. Okay? All right, so we're doing a really basic example first. If you take a look at this one, the length along the sides, and I know you guys know formulas, that's not the point of this particular problem, but the length along the side here would be what? It would be 3 units, and then the width would also be 3 units. And I know you can get the answer by multiplying, but you can also get this particular one, and this is the goal of the particular problem, by counting. So if we count up the squares in this, how many squares do we have? We have 9. So we would say that this is 9 what? 9 square units is how we'd actually read it. 9 square units, and it's written down like this. 9, the UN, or whatever the units are, and then the squared after it. But we say the word squared before. Thank you. Yes, Leah?
Why did we use, at least I did, we used to just write like 9 SQ and then the 2?
You can. It's not wrong. It kind of depends on the resources that you're using. So if you find yourself using a textbook where it writes it then that way, that's the way you would want to write it as a standard rule of thumb. I think you're going to find more textbooks using the notation like this, but they're interchangeable at least to some degree, depending on the resources you're using. It's a good question. Okay, you've probably used one of these 2 conventions before, a geoboard or dot paper. So a geoboard or dot paper can help us to think about area. And there are a couple of methods for using this kind of device to count up or to calculate area. And the addition method is one of those 2. So the addition method is area is found by adding the areas of smaller pieces. So usually what you have is some odd looking shape. It's not a square, it's not a triangle, it's sort of an odd combination of things. And you break it apart into simpler shapes in order to count the square units. And so this method is breaking it apart into simpler shapes to be able to count more efficiently. So if you take a look at this example, you'll see what I mean. This is not a square or a rectangle, it's kind of a mess. Agreed? Now, there's not one and only one right way to necessarily break this apart, but there may be more natural ways to break it apart than others. For example, if we take this piece right here, you see that there's a square in what I just did. In fact, you know what? Let me change a different color so that it's obvious where I'm marking it. We'll use blue. So here is a square right here, the blue in the top corner. You could probably find some other squares and or triangles in here as well. For example, I can take, in this case, a rectangle over here on the right-hand side. And if I do a rectangle here, not only do I now have a square here and a rectangle here, I have a triangle here too, right? Now taking a look at the bottom, we can do the same sort of thing down here. If I break this piece into a square, then I have a triangle here, and again I have this odd shape right here. Maybe it's not quite so odd, but it's simpler if I break it into a square and a triangle. So I can break most of these apart into squares and triangles, at least in this diagram, in a pretty simple way. Again, it's not the only way to break this apart, but it's one way that works pretty nicely. And the cool thing about this is that it allows you to calculate and to count the squares that are here a lot more easily. For example, my top left-hand corner the big square up there, how many units are there, square units, in that top rectangle, this one right here? There are 9. It looks exactly like the image we just saw a minute ago. So this is 9 square units. The rectangle that I formed second on the right-hand side had how many square units? This one was 2 square units. I think you were looking at my bottom one, right? The bottom rectangle? Yeah, the bottom rectangle or square would be 4 square units. Now, some of the other shapes, oh, there's one more here. These are all squares and rectangles, right? That I've marked so far. The pieces that I haven't marked happen to all be triangles. If you think about it, these 2 triangles here on the right-hand side, if I combine them together, they make a square. So you could either count them each as 1/2, or you could like put them together in some fashion and say, okay, we're just going to combine these 2 together, and those 2 combined give me 1 more square unit. You can do the same sort of thing over here. You can recognize that if I had the whole square here, it would be 4, but I don't have the whole square, I actually have a half of it. So even without counting, you can probably, and without formulas, you can probably deduce pretty quickly that this triangle right here is 2 square units. If you don't like that, you can break it apart into squares and smaller triangles and do the same thing we did before. You can do something like this. There's a square here, so that's 1. And then the 2 triangles that remain right here and here add to another 1. Right? So there's lots of ways that you can think about breaking this apart, but the crux of the issue is that when it's all said and done, you're breaking it into simpler shapes that you can count. It's all about counting it up. So if we count everything that's here, what do we have now? How many? 19. Okay, I thought I heard it 18, but 19 is what I have. Is everybody good with 19 square units total? Yeah? Good with that? Okay. So this is one way to do this, is to break it apart and add up the units. There's another one we're going to go into here in just a second. Okay, so try to distinguish the 2 differences. The reason that the rectangle or the addition method works so nicely about this one is because you can break it apart into whole shapes that are simple, that are all shaded in. Squares and rectangles and triangles. And again, there's plenty of other break-aparts that you could have done here that would have worked too. Second method is called the rectangle method. The rectangle method is the idea of constructing a rectangle around the given shape and then subtracting off the area that's not shaded in, the extra area. This method is particularly useful when the given shape contains very few full squares. Okay? So if you flip to the next picture, you'll see a little bit of what I mean. I know it's not shaded in, but the part that's inside the blue outline there is not particularly convenient for breaking apart into squares and rectangles and triangles, right? It's sort of odd shaped. And so instead of breaking it apart and adding things up, we're going to encompass a rectangle around it, and we're going to subtract pieces off. Okay? So take a look. We want a rectangle that goes through all of the corners, something like this. So my purple rectangle, how much area, how many square units are inside of this purple rectangle the way that we've drawn it? 12. So our idea is to start with 12, and I'll leave the word units off for now, and we're going to subtract off the pieces that don't get included. Now what does that mean? Well, it's going to look and feel a lot like what we did just a moment ago. We're going to box off the pieces here that are not supposed to be shaded in. In other words, if you notice here, there's one square right there. It's totally not inside my shape, right? There are 2 over here and 1 here. So there are definitely 4 full squares, right, that need to be removed. Everybody agree with that? Everything else is a partial, but those are 4 full squares that do not get included. So in some sense, we have 12 minus 4 right off the bat. Everything else is going to be our best approximation, okay? We'd like to be able to put things together that sort of look like they finish out a shape or finish out a square. For example, if you take a look, let me shade in these different colors. If you take a look at this piece right here, obviously it's not exactly, in fact, it's not even a triangle. It's not. It's a trapezoid because it's got this tiny little piece on the top that's flat, right? But if I were to combine that with this piece right here, they're getting awfully close to forming a shape that looks like a rectangle, right? They're not perfect, but they're awfully close. They're awfully close to how many square units? 2. Again, the goal is not to be perfect. It's an approximation, but it's about 2. So these two combined here are about 2. And we're going to see if we can combine any others in the same way, okay? For example, let's say if we combined, I'm kind of a fan of color today, so let's go green. If I combine this piece and this piece, those are about 1, right? They're almost each half of one of these square units. So those green pieces together, those I would say are about 1. Wouldn't you agree? And potentially the same thing happens with the last leftover piece. If I were to combine this piece right here, apparently I'm using pink now, and this piece up here, they're about what? They look like they're also about 2. So if I count what I've got left over here, I've got a 2 here, whoops, 1 here, and a 2 here for a total of what? 5? So I've got 12 minus 4 minus 5. What's that about? 3. So this is an approximation, 3 square units. Perfect? No, but it's an approximation that seems pretty realistic given the information we've done. And as messy as the picture is, there's justification for what we've joined together in the picture, either with the arrows or with the colors, depending on what you're using as you're writing, to show what you've removed and where. Does that make sense? Now, this picture really should look quite different to you than this one. You really should be able to look at those and be like, okay, like I could do the big old square thing around this one, I could do the rectangle method with this one, but it's not really like necessary. I have enough inside of it that I can count up to make that sort of an unnecessary one. But over here, there's really not a good way to break apart what that picture is on the inside into specific squares and triangles to make that work very well and to use the addition method. Emily?
More beneficial to do this on like just when there's more outside of the same.
Yeah, and there are times when it will tell you too. It will be very specific and say, so you need to know which one's which. The addition method is breaking it apart and adding up what's inside. The rectangle method is putting a rectangle around it and removing what's on the outside. So there are different methods, and they will have different names when you're given a specific method that you need to use. All right, a few conversions are what's next, because conversions is like what this chapter is all about. Conversion. All right. So these are some standard English units for area. A square foot, a square yard, and a square mile. All right, so your square foot, well, a foot is actually 12 inches, and if you take 12 times 12, you would have 144, so that's where that one's coming from. So 1 square foot is 144 square inches. 1 square yard, well, a yard is 3 feet, so 3 times 3, there's your 9. So 1 square yard is 9 square feet. The mile one's pretty ugly. If you'll remember, those were pretty large numbers we dealt with before. So 1 square mile is 3,097,600 square yards, or 27,878,400 square feet. Big numbers to deal with, right? And just like we did when we were doing linear measurements, we noticed that we've got, I want to say odd as in odd versus even, but we have odd as in they're all different numbers when we're doing English conversions, right? English conversions, while we're all very comfortable with them because you've grown up with them for the most part, they're not real easy to work with because they're all different. And again, while metric may feel a little bit uncomfortable because you haven't used them your whole life, they're very easy to work with because they're all ones and zeros. And man, zero is like the best number ever, right? I was trying to work with my son over the break on multiplication. He'd have 2 times 6, 20 times 6, 200 times 6, and I keep telling him zeros are wonderful. You just put them on the end, right? Zeros are great. And they're great here for the same reason, is that they're easy to do conversions with. So we have square kilometers, square hectometers, square decameters, and so forth all the way down. And every time you're doing it, what you're seeing is you're seeing a base 10 value times itself. So when you multiply 12 times 12, you get 144, and that's sort of this odd awkwardness back in the standard units. But here, you multiply 10 times 10, and you get 100, which is zeros and ones, and that's just wonderful. So you have lots of zeros and ones here. You'll jot those down. I'll make sure, just let me know when you're done. Do you have a question, Erica?
The last one is 5 zeros before the point zero.
Yes,
Okay, kind of.
that's correct.
On it from far away.
Yes, it is 50. It's a decimal point, 5 zeros and a 1. Yes. 1's 3 and 5 zeros. Okay. You guys want to take a look at how we're going to actually use these conversions now? Yeah? Okay. This chart's all well and good, but I don't use anything in this chart. So I'm going to show you how you can not use this chart and use the linear chart you had before, because if there's anything that I would hope that you would learn from my math classes, maybe not this is the only thing, but it's certainly of high value to me, is that memorizing formulas and memorizing conversions, memorizing stuff is probably not the best way to learn it, because you're going to forget it over time unless you're using it on a regular basis. So I'd rather you memorize as little as possible and be able to use those things more regularly. And so that's how I'm going to show you to do these conversions. Sound good? Okay. So what I want you to see on this one is that there's a square foot to square yard conversion. And yes, there is a square foot to square yard conversion here, and it's not a complicated one. I get that. But I'm showing you a simple one to start with so you can show you how to be able to do this with more difficult ones in a moment. Okay? So here's the idea. We're going to start with 3,000 square feet. And last time we talked about, I think you call it fences, Emily. Was it yours that you said that you've heard of them? It's called fences before. Somebody else used something else.
Train tracks.
Train tracks. And the language that I've always used before was, why did I forget it? That's great. Dimensional analysis. That's the fancy one. That's what you want to say in the CAF when you're talking to somebody about what you did in math class today, dimensional analysis, because that's super impressive. Okay, so here's the deal. We talked about the fact that if there are feet that you're trying to convert, then you have to put the feet in the denominator to cancel them. So I'm going to put feet down here. And your goal is to create something in yards. I know they're all squared, so just ignore that for a moment. But you need yards when you're done. Everybody good so far? And what we did last time is we recognized that there are 3 feet in 1 yard. That's the conversion that you know. You don't have to think about it, I hope, at this point, because it's something you've kind of grown up with. Okay? Now, here's the cool thing, and here's how I always think about doing these conversions. I just want it all squared. Okay? So if you square this here, then what you actually see is this 3 squared gives you a 9. And now you're probably thinking, that's silly, who cares? I could probably have done that without you showing me that way. It's not a terribly difficult one. Okay, but if you're dealing with the mile squared one, that might not be a true statement, because I will tell you what, there is no way I'm going to memorize the number that's on the bottom of that list. I'm just not. That's not worth my memorization. There's only a limited amount of space in my head, and this number's not going in it. All right? You guys, you understand what I'm saying. You got too much going on to memorize this number, agreed? And you have limited amount of space in your note card. You don't want to write it down there either, do you? No, you do not. So this method of squaring things is a very helpful method to be able to use what you already did and just extend it a little bit further. Now, the process is still the same. I end up canceling my feet and my feet squared here. And I end up with a 300. If I multiply 3,000 times my 1. And I end up with a 9 on the bottom. And what is 3,000 divided by 9? Grab a calculator and we'll put a repeating bar atop something and so forth. Did you get it, Emily? And because we have right here the yards and the squared, this is in square yards. So our solution, our answer is 333.3 repeating yards. Or if you wanted, you could write it like this. Sorry, that should say square yards. I left my squared off. And that would be a fractional sort of version of the same thing. Brianna says no thank you. You like the decimal there. As long as you have the repeating bar on top of the 3, I'm good with it, okay? So either of those answers would be acceptable. All right, so that's all fun and stuff and whatever. But let's take a look at the way it works when we actually are in the metric system, because we had this cool thing we could do with the metric system before that meant that I didn't have to put any fences or train tracks or dimensional analysis into play, right? All I had to do was move decimals around. So let's see if after, man, it's almost 2 weeks, if you guys remember the letters in order. Don't look on your paper. See if you can tell me. Okay. Some of you are mumbling, and I'm not sure if you're mumbling because you don't know or if you're just trying to pretend to go along with the flow of things, but this is it. Some of you definitely had it written down or thought through. King Henry died by drinking chocolate milk. At least that's one version of it, okay? So what I'd like for us to do is to think about that listing of the letters, and notice that we're supposed to be going from kilometers here to centimeters. So kilometers is right here, and centimeters is right here. So how many moves to the right does it take to turn kilometers into centimeters? 5. There are 5 shifts here, right? 5 moves. But here's the cool thing. This is just so exciting. You guys ready? We just do it twice because it's squared. That's the deal. We would have moved it 5 times if we went from kilometers into centimeters or kilograms into centigrams or whatever. 5 times. But since it's squared, we do it twice, which means instead of moving the decimal 5 times, we will move the decimal 10 times. And that's it. So we started out with, wow, this was a big number, 378. Thankfully, our decimal is going, well, no, it's not. Which direction is our decimal going? To the right, because I went from kilometers on the left to centimeters on the right. So here's our decimal point. It's supposed to move 10 places, and it's right here, which means I'm going to end up with 10 zeros that I need to have over here. Yes? Ask your question, Eric. It's okay.
So how did, like, if it was different measurements, like if you had only moved over 3 spots, how would you?
3 times 2, 6.
Okay.
However many spots, you double it.
Okay.
Yeah, and the easiest way to sort of justify, or maybe not the easiest, but the clearest way to see the justification is by moving it 1 spot. If you were just moving from kilometers into hectometers, for example, you'd move it 1 place, right? Because you'd be multiplying by 10. But if you notice over here, you're not really going to be multiplying by 10, you're going to be multiplying by 100, right? To go from 1 spot to the next. So you're multiplying by 10 twice, so you're doing it twice. So you're doing that on any kind of conversion. No matter how many places you go, you're going twice that many places. So we went 5, now we're going to go 10. Hannah.
So it's when we're doing it, like we need to do the picket fence when it's like we're working with multiple different types of, like
Yeah.
we're working with things that aren't in the metric system.
Exactly. The metric system's great for just moving decimal places. The fences, the train tracks, the dimensional analysis is when we're using standard units of measure. These English measurements that don't have the tens. And you can use the dimensional analysis with the metric. You can. It's just kind of overkill. You don't need it because it's so much simpler to just move decimal places, so it's not necessary. Yeah. All right, so I don't know what I'm at here, but I've got 378 followed by 10 zeros. Now I'm going to go back and try to put my commas in the right place. Okay. That's millions, billions. So it's 3.78 trillion. That's what this is. 3.78 trillion. 3,780 billion. What? What are my units? Centimeters squared, or square centimeters, right? So that's a fun expression right there. Okay, and we're going to pause right there for today.